So recently a huge hit at the movie theatres has been the film Dune. And inside Dune there are a bunch of scientific concepts, a lot of things that cause a lot of excitement, like interstellar travel. But there's one aspect of Dune that I think is a little bit overlooked and actually poses a very interesting scientific challenge and involves a lot of actually quite complicated scientific concepts that are well worth studying. And that is actually the dunes themselves. Now, this may not be the sexiest topic to discuss from the film, but one of the consistent themes I hope of my videos is that science is not just about doing what captures necessarily the headlines, it's about fundamentally understanding the way that nature works. And the reason that I want to focus on the formation of dunes is because that is a process that involves a lot of science. And although it looks straightforward, it's all very tangible, you can see it, you can touch a dune, and we're all very familiar with them. The actual process by which they formed is mind-bendingly difficult to describe with mathematical accuracy. If I contrast that to interstellar space travel, well, actually the equations for rockets and so on are somewhat straightforward. And therefore to a scientist like myself, although the concept of interstellar space travel is interesting, the actual science of dune formation I actually find more intriguing. Before we get into the formation of large sand dunes, I want to first deal with the smaller patterns that you might see on the desert floor. If you've ever been to a desert, and I recently was in a desert in Neimangu, you'll see that even on flat areas, there's like a ripple effect on the sand. Why does this arise? Well, if you had a pile of sand on a table and you blew at it, it would just blow away, right? And if you think about it carefully, it's somewhat curious that you would have a ripple effect, a little bit like waves on water on sand. Sand is an interesting object because it appears both to behave as a solid, you can pick it up, but also a fluid by forming those wave patterns on its surface. How exactly do they form? Well, it's the interaction between the particles of sand and the wind, of course. What happens is that sand is just the right weight and size to be picked up by the wind, but not to be blown away. It tends to blow a few inches above the surface of the sand when the wind picks it up. Now, how does this help the ripples form? Well, what happens is the following. The wind will pick up the sand. So if this is the surface here are the sand grains, they get picked up by the wind. The wind can't carry them too far. Eventually gravity wins and pulls the sand down, and they'll impact the sand, say here. Now, sand is a coarse material and can stick together, of course, and so at certain points you'll find there are little bumps where sand grains have got caught. And because these are slightly higher, they'll attract more sand grains, and so what you see is that as the sand bounces along the ground, there are areas where more sand grains will form, and that causes the ripple effect that you see. Right, so here will be like wave fronts here and here. The stronger the wind is, or the lighter the sand is, the further away these crests will be, and vice versa. The reason I talk about this is because it's the first way of understanding exactly how a dune is formed. A dune is a crest that's actually just very, very large in size, but there's a slightly different process that forms, although the principles are very similar. To form a dune, you need three things. You need wind, you need sand, and you need an obstacle. The obstacle, like here, catches the sand grains in a certain place, and the sand gradually builds up as more and more grains hit that location. But dunes have a slightly different property to them. As the sand gets larger and larger, if we imagine a larger dune that looks maybe a little bit like this, just an artist's representation, what happens is the wind, as it comes over the dune, has this kind of profile. These are the wind. This is where we get involved in the science of fluid dynamics. In fluid dynamics, the fastest point of the wind on this sand dune is approximately this location. This is where the wind is the fastest. And so what you find is the wind is strongest or fastest here. It will basically push sand up, particularly from this location, push it up on the top of the dune. If the wind was fastest at the top, it would effectively just blow the dune away. The reason that the dune can maintain this kind of form is because the wind is fastest not at its peak, actually slightly lower down from the crest, and therefore the sand is continually deposited on top. This helps the dune grow. However, as you know, dunes obviously do not have an unlimited height. There is a height limit to a dune. And how is that formed? Well, that's formed from part of physics called, well, actually soil mechanics or material science. When you form a tower of material, you'll know intuitively there comes a point at which the angles become so steep that it falls over. This is called the angle of repose. It's this angle here. This angle is called the angle of repose. Effectively, it's the angle beyond which this can no longer maintain a structure and would actually collapse. Now, if you have a very fine material that you can pack very tightly, say flour, you will find that if you have a tower of flour, you can pack it very steeply indeed, because you can pack in those granules, they stick together, and therefore the angle of repose is very high. For an object like sand, the angle of repose is much smaller. It's actually around 35 degrees. Depends on the precise size of the sand, it depends on whether it's wet or not. If it's wet, the electrostatic forces between the sand particles caused by the hydrogen and oxygen molecules will hold it in a much steeper angle of repose. Beyond this angle, there will be an avalanche. The dune will collapse. And so you build up this dune and it will collapse. And then it builds up again and it will collapse. And the dune gradually moves forward. Now this is an incredibly important attribute of dunes, the fact that they are dynamic. They are moving because of this process of building up and collapse. And this actually, in this country, in China, is causing a lot of concern. It's called desertification. The encroaching sand dunes, these can move as much as 20, 30 meters a year, engulf entire towns and cause immense environmental damage. It's one of the key reasons why China is currently planting huge belts of trees across some of its desert areas in order to hold these sand dunes in place. The roots from the trees can hold the sand dunes, and also, of course, the trees provide a natural barrier. In terms of the film Dune, it is actually interesting to note that the author of this series was inspired to write the entire thing by this very process. He visited the sand dunes in Oregon, in America. At that time, when he was writing, 60, 70 years ago, the process by which dunes were moving and encroaching on cities was a huge headache for the local government, and they were experimenting with planting local grasses and so on, much like the Chinese government is doing, in order to control the movement of those dunes. When he went there, he was so amazed by this process, the process of dune formation and the way that they move, that he was inspired to write the entire series of books that later became the film that we also enjoy. And so there, the science fiction movie was born, not, as you might think, from thoughts of interstellar travel and aliens and all the rest of it, but from the simple sand dune. For those of you who are interested in science, the reason I bring this up is because whilst I can explain this conceptually relatively straightforwardly, I want all of you to understand that if you're a real scientist, right, what you want to do is try and mathematically model these things, or model it on a computer and so on, and that is fiendishly difficult, frankly. The angle of repose, for example, I want you all to consider, how would you calculate that from a theoretical basis? Of course we can do experiments and see it all fall down, but how would you actually calculate that number? When I talk about the wind going over the sand dune, how would you actually model that? Actually, one of the greatest problems in physics is the modelling of fluid dynamics. The fluid dynamic equation is fiendishly difficult to solve in anything but the most simple circumstances. Even our greatest supercomputers struggle with some fluid dynamics environments. And of course, even modelling the blowing different particles of sand across the surface of the desert is a hugely complicated problem. The reason I mention all of this is simply because if you're a scientist, you have your concepts, but when you have to boil it down to making the mathematical equations and so on, it can be quite difficult. And even the most simple and beautiful of nature's processes can pose a huge challenge for the human mind.